Ask your friends to join the class. I'll start the class in a minute. Okay, I'm sharing my screen, okay? So today we'll start with zero force member, okay? Audio and video is okay? Is it okay? Abrisha, Deepak, what happened? Sanjam, Toko, Rohit, are you there? Okay, okay. Is it okay? Okay, so let's start. So we'll see the zero force member in the trusses, okay? Which member, how can you find that which member will have a zero forces? Can't hear. Okay, I'll increase the volume. Okay, let me know if it is visible or it is audible or not. I'll increase the volume. I'm sharing once again, okay?
In this session, we're going to talk about zero force members in trusses.
Now it is okay?
What are they? Why do they come to exist? And how do we identify them? What is a zero force member? When analysing trusses, we
Audio
may
and
come
video is
across
okay now?
members that carry
Okay.
no force.
So we'll start with
These
zero
are...
force member, okay? How to find zero force member in a truss.
In this session, we're going to talk about zero force members in trusses. What are they? Why do they come to exist? And how do we identify them? What is a zero force member? When analysing trusses, we may come across members that carry no force. These are called zero force members. Why are there zero force members in trusses? Naturally, one might question the rationale for having such members in a structure. If a truss member does not carry any force, why have it in the first place? There are two main reasons for encountering zero force members in trusses. 1. A zero force member could act as a bracing for preventing a force-carrying compression member from buckling. That is, a zero force member adds stability to the structure. 2. A force having a magnitude of 0 could develop in a member at some point in time when the structure is subjected to a time-variant load. Let's examine this scenario in more detail. Bridge structures are generally designed to withstand the load of moving vehicles where the load position changes as a vehicle moves across the bridge. Suppose we have a truss bridge consisting of 5 joints along its bottom chord. As a vehicle starts travelling on the bridge, the applied load position changes. At time t1, the load is distributed between joints 1 and 2. At time t2, the load is distributed between joints 2 and 3. At t3, the load is applied to joints 3 and 4, and so on. This moving load pattern continues until the vehicle leaves the bridge. The bridge truss must be analysed under each loading case. Note that a truss member that actually carries an axial force in one loading case may become a zero force member in another loading case. For example, when the load is applied at joints 1 and 2, the vertical member attached to joint 4 carries no internal force. When the applied load moves to joints 3 and 4, the vertical member attached to joint 2 becomes a zero force member. The ability to identify zero force members in trusses is important for two reasons. 1. It speeds up the overall analysis of the truss. 2. It helps developing a better understanding of how internal forces are distributed in a structure. How do we identify zero force members in a truss? There are 3 basic rules for identifying zero force members without resorting to any calculations. If a truss joint is not subjected to any applied loads and is not supported by a pin or roller, then the following rules can be applied repeatedly to identify all the zero force members. Rule 1. If the joint connects two members only, where the angle between the members is different than 180 degrees, both members are zero force members. If this structure, joint F, connects two members only, there is no load or support at the joint, therefore both EF and CF are zero force members. Rule 2.
So the rule number 1 will be the member which won't carry any load or support, that will be your zero force member. Okay, so here CF and EF will be your zero force member because there are no any loads and load is not applied in these members and there is no support. Okay, so this will be your zero force member. So if a truss joint is not carrying any loads or not supported by not supported by a pin or roller support, then that will be your zero force member. Okay, that will be your rule number 1. So let's see the next rule.
The joint connects two members only and the members are collinear. That is, the angle between them is 180 degrees.
Okay, if a member makes 180 degree angle, okay, if this see here the angle is not making 180 degree, but here if the angle makes 180 degree, then also
And one of the members carries no
will be
internal force, the other one is also a zero force member. Consider the two members AB and BC. If the force in member AB is zero, since the members are collinear, BC is also a zero force member.
So in this example, your AB and BC will be zero force member. Okay, because the angle made by this joint is linear, or you can say 180 degree. So this will be AB and BC will be your zero force member. Now let's move to the rule number 3.
Rule 3. If a joint connects three members only and two of the members are collinear, then the third one is a zero force member. Here, joint D connects three members. Two of the members are collinear, therefore CD is a zero force member. Let's look at a few examples.
Let's understand with an
Here,
example.
Rule 1 applies to joint D. Therefore, CD and DE are zero force members.
No load at D, no support at D, so angle is not 180 degree, therefore CD and D are your zero force member. Okay, there are no loads, no support.
Also, Rule 3 applies to joint H. Hence, BH is a zero force member. If we consider P to be an axial force in a member vertically attached to joint E, then, according to Rule 3, EF is a zero force member.
होगा तो see your check your connection.
Similarly, if we assume Gx is the force in an axial member horizontally attached to joint G, then according to Rule 3, AG is a zero force member. To determine the force in each of the remaining members, the simplified truss can be analysed using the method of joints.
Let's see another example. First, draw the free body diagram. Okay, with all the
In
supports
this
and tensions.
example, Rule 3 applies to joints C, B, E and D in that sequence. Therefore, BC, BE, DE and DG are zero force members?
So in these 4 points, rule 3 is applied. Where three members are meeting and the two angles are linear. Okay, so this will be zero force member. So they have omitted the zero force member to find out the rest of the forces and reactions.
See if you can identify the zero force members in these trusses.
So try to solve these three types of problems by yourself. Okay, find out the zero force member by yourself. Okay, try by yourself. In this figure ABC, these are the three examples. Try to find out your zero force members. Okay, now let's move to another topic. Any confusion from this part? See, we are revising, right? So if you have any doubt, please clear it itself now itself. I won't repeat these classes again. Any issue, any confusion? And those who have missed the class, go through the recording. Let me share the screen once again. Now let's discuss the method of sections. Okay.
This lecture covers the analysis of statically determinate trusses using the method of sections. Please review the previous lectures before continuing with this presentation. More specifically, you need to know how to draw free body diagrams, write and solve the static equilibrium equations, and be familiar with truss analysis using the method of joints. Consider this statically determinate truss. Suppose we want to calculate the force in member CD only, without analyzing the entire structure. We can do this by cutting through a few truss members in order to split the structure in two parts. When we cut a truss member, we expose its internal force. In this case, since we have cut through three members,
What about others? Screen is visible or not? Screen is visible? Audio video is okay? So please check your network connection. Okay. I'll start the class from the starting. Check your network connection. I'll play the video from the start. Check your network connection. Okay. Okay. Let's continue.
this lecture covers the analysis of statically determinate trusses using the method of sections. Please review the previous lectures before continuing with this presentation. More specifically, you need to know how to draw free body diagrams, write and solve the static equilibrium equations, and be familiar with truss analysis using the method of joints. Consider this statically determinate truss. Suppose we want to calculate the force in member CD only, without analyzing the entire structure. We can do this by cutting through a few truss members.
Okay, sorry, I was muted. Okay, sorry. So in this method, now it is okay. I was muted. Okay, so in this method, this is a easy method comparison to method of joints. Okay, suppose if you want to find the force in this member CH, what you can do, you can cut a section. You can cut a section and you can find out the force members by drawing the free body diagram. But if you go through method of joints, to find out the force in this member CH, you first need to solve. You first need to solve the. You need to find the force member force in these members. Okay, you have to solve this joint, this joint, this joint. Then only you will get to know the force in this member. But if you go through this method of joints, you just have to cut the section and find out the reactions. Okay, let's continue.
In order to split the structure in two parts. When we cut a truss member, we expose its internal force. In this case, since we have cut through 3 members, we've exposed 3 member forces. We know that when a truss is in the state of equilibrium, the equilibrium equations are satisfied for the entire structure and for any isolated part of it. So in this case, we can argue that since the entire truss is in the state of equilibrium, these 2 parts must also be in equilibrium. That is, the 3 equilibrium equations must be satisfied for each part. To compute the force in member CD, we only need to consider one of the diagrams. We don't need both of them to do the calculations.
As the beam is statically determinate, so we can take either this part or this part. It's up to you. Okay, don't need to consider the whole section, whole truss. You can take this part or this part, as the whole truss is statically determinate. Okay.
Let's consider this diagram, for which we can write 3 equations in terms
As this part has less number of members, so I'm going with this part. Okay.
of FCD, FCH, and FGH. The equations are: the sum of the forces in the x direction must be 0. The sum of the forces in the y direction.
So we'll draw the free body diagram and we have named the member as FGH, FCH and FCD. Now we'll use the equilibrium equations to find out the reactions. Okay. So this, whenever you have inclined force, you have to resolve this one. Okay. You have to resolve this one like this. Okay, this will be FCH cos 45. This vertical will be your FCH sin 45. This will be your FCH sin 45. This will be FCH. Sorry, this will be your cos. Sorry, this will be your cos and this will be your sin. Let me erase it. This will be your FCH, as this is the angle. Okay, this is the angle. This will be F cos 45 degree and this vertical will be your FCH sin 45 degree. Okay, so resolve the forces in vertical direction and horizontal direction. You'll get this one.
Must be 0. The sum of the moments, say about point H, must be 0. We can solve these equations for the unknown member forces. If we want to calculate FCD only, we can use the third equation. It gives FCD equals negative 36K. If necessary, we can use the other equations to determine the other unknown forces. The second equation gives FCH equals negative 50.9K. Then we can use the first equation to get FGH. Note for this particular problem, we did not need to know the support reactions in order to determine the force in member CD.
So in this method, we don't need to find out this support reactions. Okay, that is the plus point or advantage of method of section.
Ma'am,
Yeah.
can you please explain the submission of moment, that part?
Okay. Okay. Mute yourself, huh? Mute yourself, otherwise it will echo. Okay. Moment is C. Moment about a point. Moment about your H. Okay. So what are the forces acting? So this is the force 36. 36. What is force? Moment is your force into distance. Right. Mute yourself. Roll number 43. Mute yourself. Roll number 43. Mute yourself. Mute him. Okay. So it will be force into distance. So 36 into 6. So this is the force into distance. Okay. What will be the next force? FCD. This force. They have taken this force into. Who is speaking? Let me mute. Let me mute him. Okay. So this force and this FCH force, the distance, they have taken the horizontal distance of this 6 meter. Okay.
But in some other cases, we may have to calculate the support reactions before we could apply the method of section to solve the problem. For example, suppose we want to calculate the tension force in member BC. We cut through members FG, FC, and BC, dividing the truss into two parts. This leads to a total of 5 unknown forces for the left diagram. There are 3 unknown member forces and 2 unknown support reactions. And the right diagram is having a total of 4 unknowns. But we can only write 3 equilibrium equations for each part. So we end up with more unknowns than equations, which means we cannot solve the equations for the unknowns. Therefore, it is good practice to calculate the support reactions before splitting the trusses into 2 parts. We can calculate the support reactions by writing the static equilibrium equations for the entire truss. The sum of the force.
So it is saying that if you find out the support reaction, it will be easy for you. Okay, it will be easy for you when you consider another means these members. When you consider when you need to find the force in these outermost members, it will be easy for you. So she is suggesting that you should find out the support reaction first, though it is not necessary. But in some parts of in some members, you may need these reactions. So it is better to find out the support reaction at the first step. If you find out the support reaction at first, it will be easy for you to determine the forces in the rest of the members. Okay.
Forces in the x direction must be 0. The sum of the forces in the y direction must be 0. The sum of the moments about point A must be 0.
So if you see the figure, so there is only AX is in the horizontal direction, so 0. Vertical AY, CY and 36. These are upward direction, so positive minus 36. Now moment about point A, this moment. So first will be 6 into 6, 12 CY. This CY force into distance. So force is CY and the distance is 12. Next, this 36. 36 at the distance of 24 meter. So this is an upward direction. It will give your anti-clockwise they are taking positive and clockwise they are taking negative. So this will be minus 24 into 36. This will be plus 2y cy. So these are the 3 equilibrium equations. Find out the support reactions from this equations. From these 3 equations you can find.
Solving these equations for the unknowns, we get. Knowing the support reactions, we are now ready to apply the method of sections for determining the force in member BC. We cut the truss like this. Now we can use the equilibrium equations to calculate the unknown member forces. Since we are interested in determining FBC only, we can calculate that force by writing the moment equilibrium equation about point F. Solving this equation.
So if I write moment of all the forces about point F equals to 0, so what will be the equation? 6 into this 36 into 6 meter distance. Okay, next FBC, the force, this is the force and this is the distance, horizontal this distance, this force, this distance. Let me note. So there are only two forces they are considering. Force of this about a point is 0. The distance of this force about a point F is 0. The force of this member about a point F is 0. So only this 36, you can take 36 into this 6 meter. Okay. Force into distance. Now this force into this perpendicular distance. So FBC into 6. 36 into 6 and FBC into 6. Okay. Equals to 0. So from here you can find out the FBC.
For FBC, we get FBC equals negative 36K. Let's summarize what we've learned so far. The method of sections is suitable for calculating a few member forces without needing to analyze the entire truss. 4 main steps are involved in using this method. 1. We calculate the support reactions for the truss. 2. We cut the truss through the target member and a few other members in order to divide the structure into 2 separate parts. This exposes the internal forces in the cut members. Hence, 1 force per cut member is exposed. 3. We draw the free body diagram for one of the parts, showing the support reactions and the exposed member forces and relevant distances and angles on the diagram.
So these are the main steps. Okay. First calculate the support reactions, then cut through the target member. Target member means in which member you have been asked to find out the forces. So you cut the member over the truss and split the truss into 2 parts. Okay, and consider the part which is carrying less number of forces. For you draw the free body diagram, you can visualize that which part is having less number of forces. Write and solve the equilibrium equations for the unknowns. So suppose this is the free body diagram and this part I am considering. So if you know the support reactions, you can use those. You can use equilibrium equations to find out the forces in other members. So once you have find out the force in this member, you can go with these 2 members like that. Okay.
4. We write and solve.
Rest of the part is same as in method of joints, but here you have to cut the section and you can directly analyze. Okay, that is the difference. But finding the force members is same as in method of joints.
Solve the equilibrium equations for the free body diagram in order to determine the unknown forces. Let's apply this procedure to solve another problem. Consider this statically determinate truss.
So this is, let's say this one more example. Let's solve this one more example. So it's such kind of truss with support pin and roller. 2 loads are applied at this point, 80 kilonewton and 50 kilonewton.
Suppose we wish to calculate the force in member EF. We start by calculating the support reactions for the entire truss. Here's the free body diagram of the system, for which we can write 3 equilibrium equations.
So summation of all the vertical forces AX plus 8T. So this is the horizontal force and this is the horizontal force. So summation of those both are in same direction, so it will be plus AX plus 8T. Next, vertical forces. AY is the vertical forces, BY is the vertical forces and 50. So AY plus BY minus 50. Okay. Next, moment about A. Moment about, this is my A. Moment about A is your 0. So there will be one movement for this part. 6 into 80. So this 80, this force, and the distance will be your 2 plus 2 plus 2, that is 6. So 6 into 80 plus this 50. This 50 is acting at a distance of 7 plus 2, that is 9 meter. Okay, minus these are in giving clockwise, so they have considered clockwise as positive, and this by will give negative movement, so they have taken minus 9 into by. Okay, sign convention is up to you. Okay, you can take any sign convention, but in particular problem, suppose in this problem if you are considering clockwise as positive, you have to take clockwise positive throughout the question. Okay, so let's continue.
Solving these equations for the unknowns, we get the values for by, ay, and ax. Let's cut the truss horizontally like this. The cut divides the truss into two separate parts, exposing three member forces, one of which is our target force. We can use either of these two diagrams to calculate the target force. Let's take the lower free body diagram.
So you
Note
can
the
take
angle that
any part, okay,
FEF
upper
makes
part or
with
lower
the
part.
horizontal axis. We have labeled the angle alpha. We need to know the angle in order to calculate the unknowns. We can determine alpha using...
So see, this is the inclined part. Okay, so I need to resolve this one to find out the forces. So I have considered an angle. Okay, distance, both distance are given to me. I can find out the angle of inclination of this part. Okay, so this distance is given, this distance is given. So your perpendicular by base is your nothing but 10 alpha. Yes, but your 10 alpha or 10 theta is what? Perpendicular by base. So perpendicular is given to me 2 meter distance. This distance from here to here, it is 5 meter. So I can find out the angle also.
Simple trigonometry. Tangent of alpha equals 2 over 5. Hence alpha equals 21.8 degrees. To determine FEF, we can set the sum of the forces in the x direction to 0. Solving this equation for the unknown force, we get...
So they have resolved in the horizontal direction and they have found out the value.
In summary, using the method of sections, we can calculate the force in a member without needing to analyze the entire truss. For most statically determinate trusses, we can easily apply the method of sections to calculate member forces. However, there are a few cases that you need to be aware of when dealing with this method. Case 1. How to cut a K-truss for calculating a member force.
So this is kind of limitations of method of sections, you can say. Okay, these are the limitations of method of sections.
Case 2. What if the number of unknowns is more than the number of equations? Case 3. When using the method of sections, can we cut away a single joint? These cases are discussed in the supplementary material for this lecture. Here are a few exercise problems.
Okay, you can do these problems. Take a screenshot. You can do this. You can practice these questions. Then it will be more clear to you method of sections. Okay, and complicated sections are not required. So you just go with these kind of problems. Any confusions? So we have discussed. We have revised method of joints, method of sections also. Okay, please go through the recordings of the classes. You can write your roll numbers in the chat box. I'll call out the roll numbers. Please check. Okay. 1, 22, 45, 30, 7, 29, 33, 12, 26, 9, 4, 34, 20, 43, 2, 3, 25, 21, 17, 19. Anyone left to write their roll number? 18, 43. Okay, hope everyone wrote. Okay, 11. Okay, I'm ending the meeting. Thank you.